Good morning, everybody, and what we're doing today is rates of reaction lesson 2. So this involves collision theory. Okay, so there's rates of reaction lesson 2. This relates to the AQA GCSE specification. So if you're studying the AQA course, then this is more than suitable for you. If you are studying other exam board specifications, then you just need to double check that everything we're covering is what you need, and if there are other things you need, then you'll need to find those elsewhere. Right, so some of the resources available to students that I teach at school. The resources there on the right. Okay, we've got all those things that we can do for this lesson, and then also the book references that you might need if you want to look up any work later on or any revision. So the specification. Last video I spent a long time going through this and the lesson objectives. I won't be doing that because that does take quite a bit of time. The main thing you need to know from this slide is the students should be able to part. Okay, so it's got students should be able to predict and explain using collision theory the effects of changing conditions of concentration, pressure, temperature, and the rate of reaction. Okay, these are things that we're going to be learning over this lesson and the coming lessons. Okay, so I'll leave that there. You can pause the video now if you want to read that. All right, again, lesson objectives and outcomes. I would go through these in a lesson normally. Today, what I'll do is I'll allow you to pause the video if you'd like to go through those now. All right, so start of the lesson proper. What we're going to do, we have a quick little test here. Now, this is an exam question, so what do we already know from previous lessons? So previously you've learned about energy changes, and you will have seen graphs like this. And I just want you to have a go now to label those parts A, B, C, D, and E. So pause the video now and have a go. Right, well, hopefully you've come up with A being the reactants. That's the line that we label as reactants. B there, okay, is the overall energy change, sometimes written as delta H. And you can see that B is a line that goes between A and D. So when we find out what D is later, we already know that A is reactants. C is the activation energy, and the shorthand for that is E with a subscript A. So subscript just means it's slightly below the line. And so we also saw activation energy on that starter slide on that graph, where it was the vertical line, and the particles to the right of it had lots of energy. Okay, so activation energy is represented by line C. D is the products. Okay, so now we know that the overall energy change, line B, is between the reactants and the products. All right, and then the activation energy, C, goes from the reactants to the top of the curve. Okay, and then we've got line E, which is the energy released when new bonds form, and that goes from the top of your activation energy down to your products. But what is activation energy? You should be able to remember this from previous lessons, okay, that you've done on energy changes. Just think about it now and pause the video for a moment. Good. Activation energy is the minimum amount of energy needed for particles to react. It's very important that you always use the term minimum. Okay, in an exam, quite frequently there'll be maybe 2 marks for this question, and a lot of students drop a mark because they don't put that it's the minimum amount of energy needed for particles to react. Okay, so really, if you're making notes, really highlight the fact that you need to underline minimum, because you do definitely need to say that. Right, so why is it that when particles are moving around and bumping into each other, why do we get reactions? Okay, there's 2 things we need to think about. There are 2 factors needed for particles to react, and this is what collision theory is based on. The first factor is that particles need to collide with enough energy. We've just seen that, okay? The activation energy, the minimum amount of energy particles need to to collide with in order to react. So we know that particles need to collide with enough energy. That's the first thing. The second thing, we're just going to go through an example here and then see if you guys can actually come up with what the second thing might be. Right, so here we've got a carbon monoxide molecule, the CO, and the oxygen molecule, the two O's. In order for these two molecules to react, the carbon actually needs to collide with the oxygen. So in the picture we've got there, will there be a reaction? Hopefully you said no, there wouldn't be a reaction. Okay, so what's the problem there? What needs to happen for a reaction between those two molecules to take place? Good. Well, hopefully you've said that they actually need to collide. The carbon needs to collide with the oxygen. All right, in order for the reaction to actually occur. So from what we've said there, we've said that the particles need to collide with enough energy. That was our first point. And then the second point here, we've kind of described in pictures. So do you know what that second point would be? Pause the video and have a go. All right, particles need to collide in the correct orientation. We've seen in that first diagram, if the oxygen hits the other oxygen, there's no reaction, even if they collide at the right speed. Okay. In the second diagram, we've got the carbon monoxide molecule is turned round so that the carbon is actually bumping into the oxygen molecule there. And if they're colliding with the activation energy with enough speed, then they will react. All right, so there's the two things there. They must collide with enough energy, which we call the activation energy, the minimum amount of energy needed for particles to react, and they must also collide with the correct orientation. Okay, so thinking about what we've just said, do all particle collisions lead to a reaction? No, they don't. Good. So particles need to collide with enough energy to react, so they need to have the activation energy, and they also need to collide in the correct orientation. So an example of this would be the gas taps at school. Okay, if you go to a school or an education establishment where you use gas taps in your labs, if you turned one of those on when the gas was on, the gas would come out into the room. Okay, but there wouldn't be any dramatic flame. Now the reason for that is because those gas particles, the methane, it is actually colliding with oxygen in the air. Okay, it's colliding with enough the right orientations. Okay, they will be bumping into each other in the right way, but they don't have enough energy. They haven't got the activation energy, and that's the reason why we as scientists have to actually light the gas. Okay, what we're doing there by lighting the match, and the heat from the match is providing that activation energy. So it's giving those particles more energy, so they collide with the activation energy, and then they actually react properly, giving us our flame. All right. At that point, the flame itself will then provide the energy to the other molecules in order for them to have the activation energy, and it's a self-perpetuating reaction. Right? If we didn't have the flame, then those particles would just bump into each other. Even if it was the right angle, there wouldn't be enough speed. They wouldn't have the activation energy. Right, so linking this back to rate of reaction. Okay, so we've said previously how we can measure rates of reaction. And what we've got here, the rate of reaction depends on two things. So how frequently the particles collide with the correct orientation, all right, and also the energy with which the particles collide. So we can affect the rate by affecting these two things. So we could either try and affect the frequency of the collisions, or we could try and affect the speed of those collisions, so to get more particles with the activation energy. And in some scenarios, we could try and affect both. All right, so there are several factors that you need to know that will influence the rate of reaction, and those are the things that we'll be covering over the upcoming lessons. We'll be looking at each of those factors individually. Okay, but just remember that rate depends on the frequency of the collisions, okay, and also the energy with which those particles collide. So they need to be colliding frequently in the correct orientation, and also they need to have the activation energy in order to react. So what we're going to do now, we're going to try and link the collision theory we've been talking about just there with the reaction graph from the last lesson. Okay, you might remember this from when we looked at measuring rates. So we've got the volume of gas produced on our y-axis and the time along the x-axis. So remember, rates is all about how much of something's happening in a particular time. So reactions don't go at a steady rate. If it was a steady rate, we would see a straight line going from 0, 0 up to the top right corner. Okay, be directly proportional if we had a steady rate. What I want you to do now is describe how the rate changes during the reaction. So pause the video now and just try and describe how the rate changes during this reaction. Okay, good. So a description literally is just saying what you see, right? Saying what's happening. You don't have to give any scientific reasons why, you just have to say what is happening, all right? So it can be very, very simple. So at the start of this reaction, initially the rate is fast. We know that because the line is steepest. So where the line is steepest, where the gradient is steepest, then that is where we have our fastest rate. As it goes on, the rate gets slower. Okay, the line starts to flatten off. Okay, it's not as steep. Okay, our gradient's not as high, so the rate is slower. And then ultimately it flattens out completely at the top, and that's where the reaction stops because no more gas is being produced, so the reaction must have stopped. Right, in the classroom, what we'd do now is discuss with the person next to us how collision theory can be used to explain the shape of the graph. So we've just described it, and now we were going to discuss how to explain it. So give scientific reasons why at point A the rate's fast, at point 2 it's getting slower, and then at point 3 we've got the flat line. So you need to give scientific reasons why that's happening. So have a go at that now. Right, so here we go. We're going to use collision theory to explain the shape of the graph. Now then, something to help you here. There are the 4 boxes are showing how the reaction goes. So at the start, we've got our blue particles and our red particles, and they are our reactants. All right, and then on the far right, we've got a whole box of purple particles. Those are our products. And as you can see, as the reaction progresses from 0 to 25%, we've got a couple of our products that have been made, and the number of our reactants has gone down. As we progress to 50%, there's more product and less reactants. 75%, there's lots more product and just a little bit of reactants left. And then at 100%, we've got full of reactants. Now remember, rate depends on how frequently particles collide and also whether they collide with the activation energy or not. So what we're going to do now is try and write a paragraph using collision theory to explain the shape of the graph. Alright, so here's an example I've come up with, okay, to the sort of thing that you'd be expected to say. So at the start of the reaction, there are a lot of reactant particles colliding into each other. This means there are frequent collisions between the particles, resulting in that initial steady rate. So at point 1 on our graph. As the product is made, there are less and less reactant particles available to collide. So if we look at the 50% box, we've got less and less reactant particles available to collide. So there's going to be less frequent collisions between those reactant particles, which means that the rate is going to slow down. So that was like 0.2 on our graph. Eventually, all of the reactants get used up. So our box there on the right hand side, 100%, all the reactants are used up, and there's going to be no more collisions between reactant particles, and therefore the reaction stops. Okay, it's really important that you talk about the frequency of collisions. So what's happened in this graph? We've actually changed one of the factors. So as time's gone on, one of the factors that affects rate of reaction is occurring here. Do you know what factor that is? Can you think what that might be? Right, the actual factor there is concentration. So if you look at on the left-hand box at 0%, the concentration of our reactants is quite high. And as the concentration of those reactants gets less and less and less, the rate of our reaction gets less and less and less. Okay, so the reason behind that is due to the frequency of those collisions. But we'll look at that in more detail when we look at the concentration lesson. So what other factors could affect the rate of reaction? Now remember, rate of reaction depends on two things: how frequently particles collide with each other within the right correct orientation, and the energy with which the particles collide. So there's a few factors that we'll be discussing over the coming lessons that can influence how frequently particles collide, and also the energy with which particles collide. Just have a think now. Think if you can come up with 4 different factors that could affect the rate of reaction. I've already talked about one of them. See if you can come up with the others. Alright, so hopefully you probably came up with temperature. Okay, that's quite a common one that people already know. The concentration and pressure, they go together because the reasons, the kind of science behind those is very, very similar. Surface area on the left there, so if we can influence the surface area of our reactants, we can influence the rate of reaction. And then also catalysts can influence the rate of reaction. Alright, at school what we'd do now, we would draw a concept cartoon to try and explain collision theory. You can try this at home. If you're doing this at home, you could set a piece of paper out similar to what I've got here and just try and draw a cartoon with some particles to try and explain the theory behind collision theory. Right, thanks for watching, guys, and thanks for tuning in for this lesson. The next lesson we've got coming up, we'll be starting to look at factors that affect the rate of reaction. So I think the first one is surface area. So make sure you come back and listen in for that lesson.